Yeah, okay. Good morning to all the participants and our today's faculty, Sri Krishna Kumar. He is consultant in ITS. So all of you know that we are conducting this training program on systems applications for highway from 26th of September. Today is the fourth day of this ongoing training program. We have already discussed on ITS in traffic management and highway real-time application, intelligent transportation systems, its overview and usage in highways, enforcement solutions, mobility solution. So I will again request to the participant, please ask your questions whenever you feel the difficulty during the presentation. During the we have also kept 10-15 minutes time slot after the finishing of today's lecture. In that also participant can also ask the question. However, during the presentation also participant can also ask the question with the permission of our faculty sir. And today also there will be a 15 minutes time break at around 11:15 to 11:30. On the first day of the training program, I also intimated to the participant, we will also issue the certificate for this training program also, but we issue certificate only those participants whose attendance will be more than 75%. So please ensure that your attendance should be on all the days so you can get the certificate from the Indian Academy of Highway Engineers. So now I will not take much more time. I request Sri Krishna Kumar to start his presentation as well as his experience with the participants. Thank you.
Yeah, thank you, and thank you everybody. I hope you are able to hear me.
Yes, sir.
Okay, so I am able to. Are you? I'm not yet on the. So it is only IIHE this thing comes. I'm not seeing that my. I think I should take control or something.
Yes, sir.
Are you able to see me?
Yes, sir.
Okay, so I have to now screen. Okay, so here I am. So let us start the presentation. You are able to see the presentation?
Yes, sir. Visible, sir.
Very well. And now we can go ahead doing this.
Yes. Sir, full mode पे कर दीजिए. Sir, full screen. Yes, sir.
Now it's okay?
Yes, sir.
Now it is full screen and everybody can see?
Yes, sir.
Good. So this is a series of the training program for ongoing officers, which is being conducted at the, by IIHE. And I am happy that, I'm able to see this presentation going with all of you. And let us see now, we will get going. So this is a topic which we will be discussing today, AI-based signaling and city mobility solutions, which have this adaptive signaling and hybrid simulation modeling and city mobility plan and things like that. Now, the first, let me first tell you, these are the contents that I will be taking. This is limited to 7 chapters, and we will go it one by one. First, let us get the bearings of what is ITS and how we are actually, going to handle the ITS stuff. Everybody, in your presentations and things like that, so far, you have been hearing about intelligent transport systems. So I think there are at least 36 definitions published by the handbook of ITS. But then everybody wanted to look at ITS as a interpretation that one would like. A civil engineer will say that that is what will help me to improve my capacity utilization. Like that, different people from different perspective. As a electronics and computer science person, I would like to look at this as a subset of information technology. ITSC is about providing information to motorists and aid traffic management, resulting smarter use of road networks with knowledge management. Knowledge management is one thing which we will cover these topics in detail as we get going. And undoubtedly, this is the most cost-effective tool available to the traffic managers today. Putting a signal cost maybe ₹1 million, and putting a flyover that would cost you maybe 330 million or 300 million. So this is the cost effectiveness with respect to traffic control management. Now, why do you need ITS? Why do we need ITS? Let us take a road which is in the outskirts of the city, which is actually traveling, carrying traffic. Much before the rush hour, there may be 7 o'clock, we find that the vehicles are going on that highway at around 75 kilometers an hour. And we are seeing around 1,700 vehicles going per hour. When the traffic is going so smoothly, the traffic slowly builds up. By the time it becomes 8:39, the traffic becomes high. And then the speed comes down to 55 kilometers an hour, but the traffic volume is 2,400 vehicles per hour. As the time passes, as a peak hour is approaching, the speed come down to 35 kilometers per hour. Even that at some of roads is considered to be a good speed, but I am talking about a regular typical scenario. And then the vehicle volume traveling at a point per hour becomes only 1,700. Now, what is that you can take from here? This is the same volume of traffic much before the rush hour and at the peak hour. But a completely different situation. Why is this happening? This is the problem that ITS is trying to address. There is a very famous, procedure. It's called the Department of Transport, Washington. They have made this experiment. You take 2 jars of, 1 liter capacity funnel, and it have a funnel. And under that there is a jar, and you take 1 liter of rice and 2 funnels. What the professor is asked to do is, he is asked to close the exit of the funnel and pour the rice through it. And once the rice is filled up, he takes hand from the orifice and the rice start falling down. And the student is asked to pour the rice in a way that it is going smoothly through the orifice outside. Now, the question is how these are now getting timed. In the first instance, when the professor closes the exit of the orifice of the tunnel of the funnel, and then fills the funnel with rice and leaves it, it took him 40 seconds at that particular instant with the diameter of the funnel. In the second method, when this lady poured it directly through that, it happened. What is the time happened? It is higher? Yes, it is only less than 20 seconds. Now, this is the difference. Now, why the same space and the same amount of rice is able to travel at 2 different timings? You can get more information on this video and these experiments. And in India, they had conducted further experiments by adding stones and different kind of material into the rice to simulate behavior during mixed traffic. This YouTube will show you more information about it. So what is actually happening here? In India, whenever we have a traffic jam, you will find all the vehicles will come and join at one point, and then there is suddenly a 6-lane traffic is suddenly getting merged into a 2-lane traffic. And there you find a lot of jam happening. This is because the smooth traffic is not, the traffic is not guided so that it is able to go quickly using the available road space effectively. This is a study which conducted in the early 2011-12, where I was also a part in this thing by a company called, there is a company in Brisbane, which is Transmax. They had a project in the Vic Roads. Victoria Roads is in the part of Queensland. There is a highway on which the traffic is going, and at one particular time, the occupancy, the whole traffic gets breakdown here. And then a ramp meter was introduced to break up. You know what is a ramp meter? In India, we hardly use it, but we often understand, when there is a flyover, to be climbed up, in Delhi, if you want, just coming out of the airport and wanted to get into the first flyover, you can find a big jam because there is no ramp meter there. And similarly, at the point of joining highways from the side roads, you will find again a jam there. These jams are managed by ramp meters. Ramp meters are signals that keep the traffic join smoothly with each other. The merging is made smooth. By introduction of the ramp meter, it is similar to making the rice particle go directly through the funnel. We find the study result average flow per hour has increased by 8%, and then the average travel speed per kilometer increased by a whopping 34.9, and more advantageously, the average delay decreased by 65.3%. This is how ITS is aiding the traffic flow. Now, what is ITS? Now, in other words, when it comes to bear down implementation, we find ITS is an integrated system which have traffic signals, driver information systems, access control, area traffic management, open road tolling, variable speed limits, fast responses to the proper incident management, and host of other applicable ITS tools. And now, step by step, we will try to understand how each of this, how we actually integrate a system and implement an ITS, and how that is going into the next level of implementation. This is a typical classic example of a urban ITS. Urban means in the cities. Of late, the difference between urban and interurban is fast disappearing, in the sense that we have more of urban things coming into interurban scenario and vice versa. In the urban situation, you have a traffic control room in the middle, and then you have an urban traffic control. Urban traffic control is the signal systems and various other things. This constituted the traffic management as we understand. And then you have a parking management system where parking lots are allotted on street, off street, both. Then we have variable message signs which will inform the road users of the. And then we have the video processing and enforcement systems, which is actually the systems which manage, identify speeding vehicles and vehicles that jump road signals and things like that. And then you have what you call the automatic fare collection systems that keeps the public transport moving. And then you have public transport systems which have priorities at signals, which get more, advantage when it goes down to the intersections and other things. And then we have electronic road pricing or any kind of road pricing where the road users are charged for using the road, depending upon the time of the day or depending upon the space available at that point of time. This is what is in urban ITS. And then you have what you call the interurban ITS. In the interurban ITS, you see that there is a lot of changes happening here. The traffic control system is remaining the same. But the key here is, there is no, traffic management other than route and lane guidance system. What we have is an emergency telephone system, which is now fast disappearing with the introduction of, mobile phones available with every driver. And then you have a closed circuit television system, which keep monitoring what is happening. And then we have a variable message system, which will keep telling them. The weather monitoring system is there, which will actually, learn about the weather and then monitor and then inform the road users about the hazards due to weather conditions and changing weather conditions that will happen on the road. Then we have an automatic incident detection system where, accidents or jams or any kind of, incidents that is not conventionally expected take place in the intersection, in the road network. Then those days we had this radio information systems. Abroad, when we used to drive in 80s and 90s, largely we depended on the, local radio station for the traffic information. But now these things have changed, and now we have Mr. Google taking you and guiding you all over the place. The basic difference between these two is that the urban system, everything keep working all the time, and everything is required to work all the time, and everything is contributing to each other for the ultimate goal of better traffic management. But when it comes to interurban system, except the automatic load collection system, all other things are just there monitoring and coming into action only when there is an incident or there is a requirement of it to come into action. These are the basic differences. And now moving on, how we will just see how the technology of traffic evolved, taking an example of an intersection to start with. In an intersection, we will find first time there is a free flow. You have an intersection in one place and then you find vehicles going smoothly without any trouble. And then we introduce a manual control there. One person stand at the point, maybe in the evening and afternoon, he will come and stay there, and then we'll start manually controlling a policeman. Then there is a signal which controls automatically during the day for different times of the day. And then we find that, one intersection traffic exiting one intersection is affecting the traffic at the other end. Then we will introduce what we call the coordinated control. The coordinated control, this vehicle's exit of traffic from one intersection will get smoothly handled in the downstream intersection. And then the next one we introduced is the intelligent control. This is a traffic responsive control. In this, we used some kind of a detection systems. We will get that into detail as we proceed. And then depending upon the traffic flow, the signal will start adjusting the timings so that and then the next is computer controlled UTC. An urban traffic control or area traffic control system is that control system in which every intersection have an intelligent signal controller, which are again coordinated through a superior system called the central intelligence system, and that will actually deliver the best traffic flow. And at the end of it, now we have ITS control. In the ITS, we have, other than the normal traffic signal systems and other things, we also have the public transport, the emergency vehicles, the events that is scheduled for the day, and then we have an automatic response system which is coordinated by the city traffic management system. So this is currently the status of ITS. Now the next chapter that we get into is the data. the data is very important, and what are the collection methods? Any system that can work well, we need a proper data collection system. Now, in traffic, to collect data, we need special methods. So let us see. ITS, why traffic data is important for ITS is about ITS actually implements intervention strategies or calculated and recommended management solutions to deliver the optimum performance of the infrastructure in the current as well as contingent, that is immediately emerging situations, the kind of predictive situations. Infrastructure or the capacity being constant, the only variable is the traffic flow parameters. So it becomes important to measure the traffic flow on a continuous basis and then take action based on that. Measurement of any problem is fundamental to finding a solution for that. This is a regular management management solutions, and today the whole management science talks about metrics and metrics and metrics. Then we have this word here, ATCC data. ATCC stands for Automatic Traffic Count and Classifier Systems. These are this data, along with speed of road network at different intersections and different road networks, sections of the network, is the basic data input for a system to actually start working with a better methodology. I hope we are going well and everything is clear. Siddharth?
Yes, sir.
Yeah.
Yes, sir.
So let me just take you quickly through what are the automatic vehicle classification and counting technology options available in India today. In India, not only in India, everywhere. But we have a special problem. All this, I'll come to that special problem that we have in India and largely that we have in our developing economies. These systems are developed, basically divided into invasive and non-invasive. Invasive systems are those systems which will actually disturb the road intersection or as we go along with each of these options, I will let you know which are of, this thing, what is. This is the first generation, pneumatic detectors. Surprisingly, these detectors came into international market way back in 70s or even early 60s, late 60s, and it still continue to be used widely. In India also, they largely depend on these systems, which actually provide absolutely trash data for India. You will find many of the NHI roads and other people, they still use for traffic management this kind of very outdated technology. What happens here is, we have the pneumatic tubes, rubber tubes, through which there will be some air passing. These are invasive and destructive. They have fixed on the road using clips which will disturb the surfaces. And when vehicles pass through the, all these tubes, there is a difference in the pressure. And there are some electronics at the other end which will sense this change in pressures and then make that into some traffic data. And typically these are fixed at every lane. And you can understand what happens when there is a cycle or a motorcycle or a big truck goes. There is a big difference. And in India, if we have one of our steel rimmed vehicles go on this, and then it is cut into two pieces. This is unsuitable for Indian conditions, but unfortunately still used. Now, typical about Indian conditions, all this, I will, when I go to the last one, I will talk about it more. So let me just get through with this. These are inductive loops. This is a kind of a thing which which actually reigned in the area of traffic detection for many, many years. What is done is at a distance at 1 or 2 inches below the road, you have a coil of, wire, copper coil. And then the two ends of the copper coil is coming to one end, and then you have a small potential difference, voltage passed through this coil. So as per the basic law, when power goes through one particular media, there is a electromagnetic field around that. And when vehicles pass through this space, they cut this flux of this electromagnetic field. When a magnetic substance goes through the electromagnetic field, as per there is a small change in the electromotive force, EMF, and there is a small change in the voltage. This signature is the pulse, is identified by the electronics, and then that pulse is interpreted as a green or as a vehicle. Now again, this particular accuracy is limited to 2 or 3 classes. For example, if an auto rickshaw and a small car goes, it makes no difference. And it is lane-based deployment, and if they don't go in the lane, you don't get anything. And of course, you need to have different loops for different types of vehicles. See, there is some kind of tuning required for them. There are self-tuned ones available or manually tuned ones available. When it is tuned for a particular threshold of EMF, it works only in it provides accuracy only within that threshold. If you make it tuned for heavy vehicles, it will work for heavy vehicles. And if you want to make it work for small vehicles like bicycles and scooters and all, then you have to tune it differently. So the same one cannot be used for both. That is the point. The next is a combination of loops and treadles. Treadles are nothing but piezo kind of a thing, some kind of a load sensing cells. You have a loop here, and then you have 2 treadles. As vehicles go from here to here, first it comes on to this weighing system or the piezo, which again work in the typical piezoelectric effect. It gives you, and then you have the electro. So this combination can do axle detection and counting, and it can count up to 4 to 5 classes. This is the most widely used technology in till recent years. It performs satisfactory accuracy on toll lanes, even in Indian traffic. Before this magnetic and other magnetic and infrared detection came up, all Indian toll networks used this particular combination for pre and post vehicle detection. It performs with satisfactory accuracy, but in the midstream, again, because of the lane system, it gives less accuracy. And again, it cannot distinguish like 3-wheelers and small cars and that kind of things that we have in India, for example. The next one is microwave. Microwave is a non-invasive one. On one side of the road, you have a microwave sensor and an acceptor. It just sends microwaves all over this and it gets back. And it just senses, and then you have to specify the road again, lane-wise, barriers and non-trafficable zones and all that. We did some trials in India when this product became available in the international market in the 90s and beginning of 2000. This is widely used in Middle East and many other countries. The basic problem is the classification of the vehicle is based on the length of the vehicle and not the axles. And the resolution is 2 feet. lane-based logic design, and there is an occlusion possibilities. Very good solution for presence detection and incident monitoring. Easy to install and can perform in extreme climatic conditions. In India, this is not used because when we tried them in Bombay, we found the distance between the vehicles are so small here. The lengths are always vehicles are always seen as continuous. Because especially on low speeds, it actually becomes very close to each other so that the system is not able to detect the end of one vehicle and the beginning of the other. So it continues measuring it as the same vehicle of a unacceptably long vehicle. Again, detection is based on the length of the vehicle, not axles. Now, these are the systems which are now expecting to be coming up. These are video analytics systems where we have there are two technologies basically. One is tripling technology where we have the original concept of loops. Fixed loops are replaced by virtual loops or detection zones. And as and when image of the vehicle passes through that detection zone, it is made into a data. And then there is a pixel modeling. Pixel modeling is that looks at the vehicle and then try to interpret what vehicle it is. We need to keep multiple cameras to cover multiple lanes. This is non-invasive. The field computation systems are very costly because the image processing is not an easy chapter, easy job now. The server based somewhere else, then you don't get online data. In India also they tried to implement this, and the very big companies try to implement this because obviously it looks very easy to implement. But they all got stuck at 92% accuracy. Best recorded accuracy is 92% in Indian environment, whereas abroad they are giving much better accuracy. These are suitable for, in India, they also, many companies are talking about AI into this. AI is only a method of computation or an improved method of computation, which is characteristically different from the fundamental thing. Though many companies claim in India, I'm actually looking at it in very close quarters, nobody could get a certificate saying that it can work efficiently, getting better than 95% accuracy in India so far. So let us hope that. And then the other problem with this is, in India, we largely go by, we go exclusively by classification by axle, number of axles, whereas there is no way of counting the axles on a CCTV, on a TV-based system effectively because of occlusion and other issues. Moreover, whether it plays a different part, a heavy rain or a fog can give you very difficult images. So it cannot work. Environmental factors, light, fog, rain, dirt, glare, insects, all computed. And the classification is limited. Another thing which came in the recent past is the 3D omnidirectional tracking. This is an activity which I am involved with. Actually, what happens is that you put a 360-degree camera here at the top, in the middle of the road, and it is looking up things from single camera coverage for an intersection. And 3D omnidirectional object tracking. See, intuitive and visual software that it have a lot of expertise like this. What really happens is, it is actually the moment it is a vehicle is going, it is able to detect the edges of the vehicle and then do a 3D modeling of the system and direct it omnidirectional. True time moments, when you have placed a camera near to the center of the intersection, it is able to see few hundred meters on all the four directions, for example. The moment a moving article, namely an automobile, is detected, the moment it enters into its zone, say at the northmost point, it is given a unique ID, and then it is tracked throughout its trajectory. So it comes into the intersection, maybe get a stop at the stop line because the signal is red, and then it turns to left or goes straight or go right. And then the system keep on following that till it exits the vision space. During this period, at one point of time, it will be right below the camera, and even a normal telephone today, camera can actually do measurements. So there is intelligence in this that can actually measure the size of the vehicle, and because of it is tracked from one point to point, it is able to see the speed of the vehicle going through the intersection. So it is actually the 3D, the 360 diagram look like a globe like this. This is flattened bird's eye view. And then using virtual CCTV or pan tilt and navigation, you can make it into quadrants for each approach. And then you can actually point and click and create. These blue zones are the detection zones, which will actually detect the presence of the vehicle. And then the vehicle goes through that. These are all IT enabled systems, IoT. So it can actually be managed remotely. The other advantage is it enables traffic data collection. It activates a reporting engine within the grid smart. This comes with the software and all. It can give you data in different forms, probably, and it can also on the highway if you want to use. You can. This is how the system works. You have a camera which is at a height, which you will see the vehicles going in the highway, and you can have it on a tripod or a strong trailer, and using solar panel you can power it, and then you can set it up and collect the data at the road section as you do at an intersection. So this is we did some trials of this product in India. This is a Ramaya Hospital Junction at Bangalore, where we did some trials for this. And, so this is very easy actually to data module works very easy. You select the system. This is a 1 minute video. This is select. You want to build a report. You see what you want. You want training movement counts. All right. 15 minutes interval. All right. Then which is the date you want? Pick up the date. And then what time to what time you need? Pick up the time. Then you simply say generate. The moment you say that, it renders a report, give it to you, and give you the classification of the vehicles, northbound, southbound, turning movement counts, everything. And you wanted it in any file, Acrobat or CSV, or now you want to change the vehicle into the classification type. So you want to change it. So how many vehicles? If you want to change the length bins of the vehicles, you can change the length. You can just click and change 7 feet to 7 into 14. So for different lengths of the vehicle, and then you can. Hello.
No, continue, sir.
So this is the data module. If you have it on the Grid Smart, it is so easy for you to create a database. And now this is how you create a data. I think you all see that. And next, I want to talk about this is turtle. I've been working in this area of ATCC a little bit, and then till I have something like somewhat like 40 years working in the area of traffic management and control. And for the 30 years, I never found a system which will actually do a proper data collection in India. The reasons are two. One is that in all the systems, traffic counter and classifier systems are developed abroad. In India, there is no originally developed system. Technologies, products, everything comes from abroad. They are all tuned or made for the traffic which is existing there, where 4 or 5 classes of vehicle go in predefined lanes. And then you don't make out the change of how this it happens. The number of classes of vehicles in India, you start from bicycles to multi-axle vehicles. So this seems to be a different difficulty. So during 2006 or 8, I came across of this product in one of the international exhibitions where there is a vehicle detection technology, which I thought might get useful to India. And I had opportunity to work with that. And now we are in a position to provide better than 99% accuracy and on Indian roads with multiple. So this few slides are on that product. This is non-invasive infrared technology. It counts, classifies, identifies a lane and measures the speed. The speed accuracy is 1 point plus or minus 1%, 2 to 2.5, that's 5 sigma. Accurate up to 2 to 9 lanes, it can give you an accuracy of 98 to 99%. The interesting thing is it can accommodate traffic with a low lane discipline, multiple classes of 200 bins, and it had a definable classification table, and it is possible to measure the wheel chord length. We'll get this into detail. Now, let me just explain you how the system works. The system have two parts. One is a transmitter, the other is a receiver. The transmitter, this receiver and transmitter are positioned on the road right few centimeters, 5 to 6 centimeters above the road surface. 5 to 6 centimeters above the road surface. So the transmitter have two torches of 108 megahertz and 96 kilohertz, two infrared rays which are passing into the receiver. On the receiver end, there are two receptors. These two receptors receive the rays coming from both the torches. So we have a pair of parallel rays and a cross rays. This is a transmitter receiver, opposite side. It have two infrared beams and it have a pair of parallel beams and two cross beams. Now, what happens when a vehicle going through this, they break and make these rays one after the other. These timings are captured by the receiver. You see, this is how when a vehicle goes through that, it makes and breaks the event. Now, believe me, this transmitter is using a processor which can actually measure things in nanoseconds. And this infrared, have the beam events are broken and made, and these have wavelengths of nanoseconds. So these are able to measure the incidence in terms of microseconds and micrometers. Vehicles in far lane can be detected, and then you'll ask a question, what if exactly two similar vehicles go? This is a representative diagram. Even if exactly two similar vehicles go in the road, seemingly, blocking the other one or shadowing the other one. Because of the cross beams, it is not going to miss any of the axles. The piece passes under the way to see the far axles near the vehicle. The indispersed beam events are interpreted by total software to determine the vehicle. Now imagine how vehicle classification is done. We have, suppose this is a 5-axle vehicle, articulated. So we will say that when you see a vehicle going in this, group one vehicle, and in this 2 vehicles nearby, and then a vehicle, and we also will specify the speed distances between them. System, believe me, the system can actually measure them in micrometer accuracy. Based on this data, we are able to classify the vehicles axle wise. And you can even measure the size of the tire used. See, for example, in India, there is a vehicle class called LCV. LCVs and big Mercedes C-Class Benz have exactly the same axle length, but they have different tires. So since the tire distances are different, then we tell them that these are different and these are different classes. So, and then the car and auto rickshaws. The axle distance of small car and auto rickshaws are almost the same, or in some cases, auto rickshaws are bigger than the small cars. But their tires are again different, and their tire positioning is different. So in 2013, we developed a special program for India using the input from Melbourne, and this is the standard scheme we developed. We have bicycles, cycle rickshaws, 2-wheelers, 3-wheelers, tractor with trailer, and SCVs. This is a small commercial vehicle. LMVs, light motor vehicle, that is the car. Here we have our Tata Nano to Mercedes C-Class Benz and big vehicles. They all come into the class 8. Then you have 2-axle light commercial vehicles, LCVs. And then you have, rigid tracks and multi-axle tracks, articulated tracks, and all that. When we published this in India, it was accepted by long people, but then we found that this needed some more sophistication, because a final classified system with over 20 classes is now available for India, starting from bicycles to oversized vehicle above 7-axle. We have, you see here, cycle rickshaws, 2-wheelers, 3-wheelers, LMVs, small axle vehicles, this Tata, all that 700 kg capacity vehicles. Then we have the tractor with 1 trailer, 2 trailers, and without trailer. These are standard, things that you see on Indian roads, especially the village roads, upcountry roads. So this system is now available with this kind of specifications to work in India since 2014. This is how the system works like. It comes in a box. You put it inside the box and put it inside here. You can put a solar panel there and it can work. It can be used in the highways or even in the intersections to measure the speed. It can be on a tripod and you can use it for portable or changing data collection system. On the road, this is how it is embedded on the road surface. You put the system here. The system comes with IP67. So even if water comes here, in many countries, we have something like 400 or 500 of these units working in India now. And in many situations, they have gone underwater. And when the water goes away, it will start working again because the product comes with water protection system and everything. On the side of the road, you can put it like this. One receiver here. and on the other side, all that you need is a small scooter battery which can work for 7 days. Oh, now I have to show you a demonstration of the turtle. Are you able to see this?
No, sir.
One second, one second. New Windows here now. Yeah. Now I wanted to share. Yeah, you are able to see a video and data, no?
Sir. Now it is visible.
Now it is visible?
Yes, sir.
Yes, sir. Yes, sir. Visible, sir.
Good. So, see on the left side, you are seeing Indian standard Indian road. Actually, this is the test when we conducted in 2013 in IIT Madras. We have done this. See, right here is the place where that turtle is placed, and here is the data that is going. Now, let me play this video. You see these vehicles going. So each and every vehicle, when it is coming, you can see them getting recorded here. You're able to see it, no? As and vehicles go. See now,
Yes,
I go here and see. Suppose I wanted to see, let us say, you can get different data on that. So, I mean, let me see. This LCV, I wanted to see where it is. See, this is the LCV. You're able to see it, no? And then after that, two-wheelers, you can see the vehicles, each one is going, then it is coming here automatically. So this is the time. I'll just come to that in a different one. You can play backwards, you can play forward, and then you can go into so now any of these things which I wanted to see, I was just looking for some options to show you how to actually see this. Let me see. So you're able to see how we are able to, this camera, this is only a demonstration thing. And now I'm taking this out, okay? Now I'm sharing you. You're able to see one Excel sheet? Hello?
Yes, sir. Yes, sir.
This Excel sheet you are able to see, no?
Yes, sir.
Good. See, this is how the typically it comes, the date, the time, the zone, the timestamp, the sequence, the lane, the speed, average speed, the speed of the axles together, the direction of the vehicle, the class number, the class name, and then axle counts, the wheelbase, the length of the wheel, the axles, the presence, width, distance, maximum distance, and then the special engineering designs as you have your headway, spacing, gap, and clearance. So almost all, more than 60–70% of the institutes offering traffic engineering courses now have got this equipment, because this is the only equipment where they can provide this vital traffic engineering parameters, which will help them to do modeling of the traffic. Okay. So this data is available even for every axle. Now, if I look at this, for every axle, you get the distance, the axle speed, axle chord length, axle distance, axle minimum distance, and axle maximum distance, the axle edge. And then if you have more axle, you get more data. So let me see if there is here you have a vehicle, and then it is 162. It's a 3-axle vehicle, so you have more axle information. And you have small commercial vehicles, and then you have MCVs, even bicycles, 2-wheelers, 3-wheelers. All kind of vehicles are getting dictated with accuracy. So this is how the data look like, right? So we go back to our presentation. Okay, now we are back to our presentation, all right? So now I have shown you a video turtle demonstration. Everybody's back and we are okay? So then we are okay?
Yes, sir. Yes, sir.
Good, good. So I'm getting back to the presentation. We have talked about now data collection and also talked about the different technologies, and also demonstrated you a system working and how the data is collected, which can be used. You can have a number of these turtles located all over your road network, all collected to a central station, and collect the data online and see the data changes everywhere. We can have even a national traffic control center with a number of traffic data collection systems, which will be feeding the data. Unfortunately, I should say that in India, we are not very data conscious, and our ministry is not data sensitive. That particular chalta hai attitude is really taking its toll as far as I understand things are. Okay. But now it is so easy for us to make We are in the slideshow mode now, right? So this is, hello everybody, we are there, and the slide,
Yes, sir.
good. This is a performance comparison of different AVCCs which I talked about in India. So far, I talked about pneumatic loops, pneumatic tubes, loops, lip spears, microwave, native video, fisheye camera, and infrared and turtle. So this is the overall ranking, and these are the tolerance. The basic problem in India is the problem of lane discipline. People and all systems abroad are designed for lane traffic. And when we started developing the system for turtle, originally, when you have defined that this is a 3-lane road, and then suddenly the system detects a 4-lane fourth traffic. Then what the system validation does is it just coolly removes that, because this is an upside data as per a foreigner. But in India, we can even find 5 or 6. So we have a separate way of doing the in the lane marking, lane defining, a dynamic system introduced for turtle, in which at one point the lane number 1 will be using one motorcycle and one car, and in the next it may be using a truck, and a 3-lane road will be using 4 or 5 vehicles at a time. So there all these things are factored in developing the firmware for making the system work. All right. Now we got into the second thing over. Now the next one we talk about is intersections and communications. This is important because now we are coming into the next. In the urban network, as you know, more than 60 to 70% of the delays are taking place at the intersections. And more than 40 or to 50% of the accidents are taking place at the intersections. So the intersections are key, or the most critical point when we actually try to tackle urban ITS. Now, conventionally, we used to have a pole in the middle and have 3 lights on 4 sides, and which will keep coming. The first generation traffic controllers used simple, thermal fuse. The thermal fuses, most of the people today won't even know about it. The thermal fuses are that, one light glow up and one glow, and then there is a fuse connected with that. That fuse get heated up, and after some time it get fused. And then it goes, and then the next light comes. It have no comparison to the what is a vehicle, what is it coming, and all that. Today, things are different. There are 3 things which is important. One is that awareness, number is connectivity, and number is data driven. See, all this advanced sensors, multimodal detection, automatic data collection, this gives you the awareness of what is required for the intersection. Intersections are connected both to the cloud and to the automatic vehicles. Even the vehicles start communicating to the traffic controller. There are advanced applications, data-driven planning, as well as data-driven operations. Now, these are the 3 components that constitute. You have detection system, you have a communication system, and you have a controller. And detection is through cameras. And this is how the intersection components are defined today. Now, today, what do I need for my detection to do? What all things I need to detection? I need vehicles, I need pedestrians, I need bicycles, because they need protection. Trucks, buses, I need buses, I need EV, electric vehicles. Why? I need to do this because this not EV, sorry, EV stands for emergency vehicles. All other things are different. So now you need vehicle detection for performing all these factors. I need vehicle detection, I need for intersection operation, traffic responsive, speed actuation, and performance measures. Pedestrian detection I need for signal performance. Multi-modal access. Bike detection also the same. Truck detection I want priority routines and things like that. Multi-modal access and emergency vehicle detection I need for preempting them, giving them priority over other vehicles when I need to cross. Today, why do I need, what do I need, and now how do I get there? To get this, vehicle detection, I can use either loops or magnetometers or radars or even video detection systems. Today, nowadays, it is largely video detection. You find small cameras. In 2009, 10, I was actually overseeing as the vice president of a company implementation of a ATC system in Bombay, which included around 250 intersections, where initially the World Bank insisted that we use loops and magnetometers, loops for the detection. But then by the time we had our pilot run, we could convince them to change detection to video. So we have something like 250 intersections. I think they did not improve it further. Video detection systems installed in Mumbai. Radars are not done, more in India because they are for speed. Then we have GPS and for emergency vehicle detection, bus detection. All the buses today are fitted with a GPS. All the emergency vehicles are fitted with a GPS. When you actually, and it is in an environment such as today, the bus company shares its database with the traffic control room, and the traffic control room knows which bus is going where, and when a bus comes to the stop line of one particular intersection, the traffic system knows about it and then try to give a priority for the bus at the intersection. These are the basic applications of loops and magnetometers. You can do the count, it can do the traffic responsive and adaptive and the special plan for the system. Now, a smart intersection is a intersection which is capable of optimizing the operations, reduce the congestion, and enhance the safety, and is ready for future. Now, why do we need all this? This is the, what, how, why system. What we need is intersection operations. What we need is synchronize the clocks to the exact time, the plan selections, central monitoring, the surveillance, the multimodal operations, the priority routines, the preemption, the signal performances. All these are done by connecting interconnections, wireless communications. This is how it is connected: cellular, cloud. And what we need, why we are doing all this is because we have data, traffic data, pedestrian data, system performance data, system alert, and connected vehicles. Now, just a few slides on how the connections happened. In the 1920s, in India, we never had a signal. I think the first signal came in India in 1959. But internationally, this is how it went off. First, we have electromechanical controllers, which I talked about. Then we have 7 in the 60s, and modern communications came in 1960s. Microprocessor-based controllers came in the 60s overseas, but in India, we commissioned the first. I commissioned the first microprocessor control system in the Abits intersection in Hyderabad in 1984. Yeah, and then we had modern, and those days we used to connect cables from one side to the other. I'll come to that technology. IP communications in 2000, you have now IP. And now we have all the cloud. This is the legacy communications where we have things going one after the other and a time switch doing that. We have a centralized synchronized clock in one of the master controllers, and that kept on giving the timing to the slave systems. These are the communication technologies now, earlier and today. We will give more into this. These are the twisted pairs. This is supposed to be modern, and now it is Ethernet. Then we had wireless technologies which replaced serial and broadband and short distance radio communication. And then you have now the latest LTE and expected to be 5G. This is a twisted pair technology which we used when I first synchronized signals. In 1989, Rajiv Gandhi came to Bombay, and by slip of his tongue, he announced 100 crore rupees for modernization of systems in Bombay, where one traffic cop could put his foot down and get 10 crores to do traffic management. So the idea was to provide a synchronized corridor from Santa Cruz Airport up to Mandralaya. And that job was, in India, there was no controller or technology available then. And Siemens, Germany supplied the controllers. And CMS, a company which I later joined and worked for some 18 years, we installed and implemented that system. And there we used this kind of communication cable. From Santa Cruz up to Mandralaya, and also some other major corridors, we have to dig and put cable from one junction to the other and make sure they work. And today, all that you do is put a SIM card in one controller and it is connected all over the world. See, life has become so simple for us. See, today, these communication technologies are changed. And then we have gone for city-wide units of different communication, the smart communication plan, the redundant communication architecture. This is the first way. We used to have, client PCs and servers, and these kind of things which we implemented in Mumbai that time, where we have different switches, and then we have put some kind of a thing. But today communication architecture is much simpler. We have this multiple rings. This is a redundant communication architecture, which is self-reliant and also self-learning and self-repairing. It increases the responsibility to near 100%. So surveillance is possible, complete data continuity, complex network, equipment costs are a little high, reliant IT. They're reliant on IT staff. These systems are called resilient systems, which are able to learn by itself. And if you have a break on any of the network, it can actually reroute the data using available other routes. This is the conventional traffic management control to each of the intersections, different way. We use all kind of Bluetooth and other communication for local communication. And then another important thing is the peer-to-peer communication. Today's communication systems are one-to-many, what do you call? See, the thing is that if you put one camera earlier, that camera used to feed into a one control room. Today, one camera can feed data into multiple control rooms. So this way we are able to, and then here that is called a special word which I'll tell you before it slipped my mind now. And now this is peer-to-peer communication. In this, what happens is that each traffic controller also communicates with the nearby controller without going to the main ones. So this kind to this. And the next chapter we have is ATC and ITS future. Now it is 11:15. I think isn't the time for the break?
Yes, sir.
Yes, sir.
All right. So we are on dot. So I think next one we have much lesser ones. Okay, but then the next chapter is a bit big. And the next, but one thing is completely that hybrid simulation and modeling is a completely theoretical one where we cannot do much of time. So I think this is appropriate time for the break. So let us take a break and reassemble at 11:30. Okay?
Yes, sir.
All right. only for a short term. There are a lot of data available in India now for traffic. We have the FASTag based tolling happening, and we know exactly, not exactly, approximately how many vehicles are going through each of the toll roads and all that. See, all this data has to get accumulated and converted into big data format so that we are able to see in the long term how these things are going to develop. We don't have that mechanism put in place so far. Hopefully it will be there in short of time. We have transport economics and traffic calming devices that is now developed. It is one of the major things in environment because the sound and pollution that happens due to vehicular traffic, AI is able to correct it a lot of ways. Today there are these UTC systems which will accept inputs, not just the traffic flow, but will also accept data from the atmospheric detectors, pollution monitoring systems, sound levels. All these are used as inputs for automation or optimization of the systems. And of course, you have intelligent roads and highway systems and what you call the forgiving designs. Forgiving designs are those designs in which even in the event of a driver making a mistake, he will not get into a grievous injury or a death probability because the system will avoid that. Okay. And I think the next chapter we will get into is the hybrid simulation modeling. This is largely a theoretical thing, and this subject, though, is one of my favorite ones, which we used for many, class studies. I think in a online course like this, I don't know how much you will be able to catch unless you have a basic idea about the basic simulation models. I'm sure you have learned about these simulation models. There are basically, in hybrid modeling approach, hybrid simulation model actually combines two or more of these, basic simulation models. A discrete simulation system, discrete event simulation, is operation of a system as a discrete sequence of events in the time and marks change of the system, change in the state of the system. These are, possibly point by point. And in the system dynamics is an approach to understanding a non-linear or a continuous behavior of a complex system over time using, stocks, flaws, internal feedback loops, table functions and time delays. So basically, difference between these two simulation models is one is discrete, the other is continuous, non-linear, and it is more complex. Whereas agent-based models are a kind of micro-scale models that stimulate the simultaneous operations and interactions of multiple agents in an attempt to recreate and predict the appearance of a complex phenomenon. In this, what happens is that, suppose, as I earlier mentioned, in a connected vehicle scenario, each vehicle is an agent, and each operation is actually going to affect other vehicles. So in driverless cars and connected vehicles, agent-based simulation is extensively used. By meaning 80% of the algorithms and simulations made for them is based on agent. And in this process, what happens is the whole is greater than the sum of the parts. It's a saying which actually emerges as it is. True to the word hybrid, the emerging system is different from its parents, although it has the characteristics of both the systems. Now, there are basically 4 types of simulation models. One is sequential. Sequential models are nothing but 2 or more distinct single method models, which are executed one after the other, but only once. so that output one becomes input to the another. Sequentially, you have a small package which actually makes an output, which will go into another, model, and that model produces another model, always in a sequential way. There is another method called enriching method. In this, there is one dominant method with the limited use of other methods. This is a process environment model as a special. SD is a dominant and D is a separate in relatively minor. Your system dynamics is a dominant model and discrete event simulation model is a relatively minor one. This is the performance of a dominant method is enriched by using other ones. Then there is an interaction model. In an interaction model, each one is distinct, but important single method submodel, but equally important. Each one is distinct and they all operate as a distinct model. And these models, the submodels that interact cyclically at a runtime. You can have a number of models working at a time, and one model is an important single method, and there are other submodels. It is essentially a top-down hierarchical method in which who has more say and which will run first, and who take from whom and who gives to whom. And the last and most seamless model is the integration model. It is impossible to tell which method, where one ends and the other one starts. Everyone agreed that what an integration means. It is a contiguous thing with no end and no beginning. It is a seamless model. It is integrating all the methods. The hydra simulation body, basically, you have a real-world problem. But the real-world problem is made into a conceptual model. This model is using the modeling. This modeling method might use multiple models and use any of the methods which we described earlier for making into a conceptual model. Once this conceptual model is made, it is verified and implemented and made into a computer model. And this computer model is verified in a situation, a scenario simulation, via experimentation, and understand the solution, whether it is correct, and then apply it to the operational world, operational validation, understand whether it works, and then inform the practice, and then that becomes an operation. There is this hybrid simulation approaches are many. This is largely an AI method, and then we have seen post 2000 there are many higher computing power. You can do multi-processing. You can do even high data processing, high volume data processing, and there are more developments taking place. The hybrid models, they themselves got integrated. In 2015-16 in Stockholm, for the traffic signal management, VISIM and MISO. VISIM is a micro model. MISO is a MISO model. MISO means, you have micro model and you have macro model. And then MISO models are those models which are in between micro and macro. MISO, a software package which is available, which uses MISO models, MISO data. So they combined the output of, they have mixed use of VISIM and MISO in Stockholm in 2016 and obtained appreciably good results for the optimization of their signal plan. This is one of the flagstone developments in the area of hybrid models in transportation. The other thing is, as I was mentioning earlier, they are capable of including multiple objective functions. See, conventionally, when the traffic management system started, the objective management always used to be improve the travel time from point A to B, or reduce the waiting time at signals, or reduce the overall delay from point A to point B. So it was always dependent on traffic and traffic flow. But today, using these hybrid models, we are able to simulate different things: cost, travel time, carbon dioxide emissions, sound levels. Many objective functions are able to get integrated in defining the objective function. Multiple. AnyLogic is another software which is an established generic software which is used for many applications, especially medical data processing and things like that, but is also used in transportation extensively. You know, the hybrid simulation approaches is a practical combination of optimization techniques and simulation models. This makes the output accessibility a grade higher. And it gets, especially for intermodal transportation. You know, in road traffic, now you are going to look at intersection design, you are looking at, how the vehicle, not only the vehicle, you are looking at the pedestrian, you are looking at the emergency vehicles, you are looking at the carbon dioxide and other emissions in the intersection, the level of overall pollution, and many other factors. So by compiling these simulation approaches, we are able to get better results in the application of intermodal transportation. Okay, that's good. Now we have only one more chapter to plan up, that is urban mobility planning. All right. I think we are at 12:09. Oh, I think we will be ahead of time to finish it. And we'll have a lot of time for question and answer. Urban mobility planning. You know, most of you, while doing your courses in your engineering colleges and those who have done transportation courses, we all did a course of visiting some town and developing a transportation plan for them. So now those plans are all done because they don't actually reflect the current situation. Today, urban mobility plans are widely used as planning tools. The plan comprises of objectives and measures towards safe, efficient, and accessible urban transport system. It is when you plan for urban mobility, urban transportation earlier, we only bothered about vehicles and their movement, logistics and their movement. But today, it is the mobility that matters. Now, in India, if the cities have to develop any central funding, it is mandatory for them to develop a urban mobility plan. Yes, it is going on for last 8 years. Yeah. Many states and cities have progressed in this regard substantially. What is mobility and what is accessibility? The mobility represents individuals' capability to move through space and time. Mobility represents individuals' capability to move through space and time. Mobility is measured in terms of how far and how quickly. Accessibility is the ability to reach social and economic opportunities, and at what cost? Time, money, comfort, the risks involved. A good transport system should be designed to provide more accessibility per unit of mobility. So this is a function of multiple town planning and transportation activities. We will see them in detail. Sustainable urban mobility planning is a new approach focusing on mobility in the cities. The difference from the traditional transportation planning, focusing on citizen mobility requirements. UMP, urban mobility planning, aims to move towards strategic, sustainable, and inclusive urban transport planning relying on data. Now, again, the big thing comes here. What is the difference between tradition traditional transport and planning, traditional transport planning versus sustainable urban mobility planning. I'm sorry, there is a spelling mistake. See now, as I told earlier, traditional transport planning focuses on traffic, whereas sustainable urban mobility, SUMP, focuses on people. The primary objective of traditional planning used to be traffic flow, capacity, and speed. Here, the primary objectives are changed to accessibility and quality of life. This includes social equity, health, management, health, environment quality, economic viability. This is mode focused. This is integrated. Earlier, we used to develop a train system. See, in Mumbai, you see, we have we have one of the proudest, traffic during our conventional electric train system. But they are developed so earlier without any, thinking about how to have the intermodal transits. You cannot go in a car, park your car and take a train. It is unthinkable in Bombay. But even places like Bombay, even the newly came up metro system have very limited parking and nodal shift available. This is what is this mode, the integrated development of transport modes and shift towards sustainable mobility. Even the last mile and all is still a big problem in Bombay. But except some places where they could afford, there is enough space like Ghatkopar and all, where you have a large parking area, because that is a terminus ever since it started working. But now with the 10 lines coming up in Mumbai, this is going to be a big challenge. And all, full with the traditional last mile connected with the queue transport of Bombay suburbs called the great auto rickshaw. Infrastructure as the main topic, whereas the combination of infrastructure, market and regulation, information and promotion becomes sectoral planning document. This is consistent with the related policy areas. Short and medium term delivery, long term vision and strategy is what is important in terms of sustainable urban development. Covering an administrative area, this covering all functional urban areas. Transport planning erstwhile used to be the domain of traffic and transportation engineers. Today it is interdisciplinary. Planning is done by experts. Now, today, urban mobility planning involves a lot of stakeholders and citizens into a transparent participatory approach. It is a limited impact assessment is done for traditional, because here it is a systematic evaluation of impacts to facilitate learning and improvement. SUMP, Sustainable Urban Mobility Planning. It's a comprehensive approach. It allows the basic needs of individuals and societies to be met safely in a manner consistent with human and ecosystem of health with equity within and between nations. So the system take care of needs of the school children. It also takes the need of old and people. It makes sure that everywhere there is a ramp for physically challenged people, ensuring their smooth mobility. These are the things which were not part of our plan earlier. Now it is affordable, it has to operate efficiently, and if it has to offer a choice of transportation options to support a vibrant economy. Today in Mumbai, transport, I live in a suburb called Thane, and it's a Hirandani estate, one of the not the well-to-do areas. And I find all the executives who live here are all commuting through an air-conditioned bus, which is on app-based. There are 4 or 5 companies operating it, and all of them books their seat. They go so comfortably into their offices. Whereas in our period of working, unless if you are driving a car or with a driver, you are sitting in the road, and or you are rushing from place to place and taking the highly difficult. So this new method of travel for Bombay, it's with air conditioned comfort and I think even some buses are even providing Wi-Fi for the people who travel. You have a plug point to charge your notebook or mobile phone. All that is provided. So you see, this is how it support a vibrant economy. When you have that kind of a choice, you don't mind sitting in a bus for an hour or two to commute to your office. So I'm sure this is going to make a bigger change again once the lines which is going through the metro lines going through this area is going to get commissioned. And of course, it contributes to environment by limiting emissions, the waste, and the planet's availability to commute them. They are minimizes consumption of non-renewable energy and economizes the resources to sustainable yield levels and do the living concepts of reuse, recycle, and minimizes the use of land and production noise. So this now again, before you start getting on a SUMP for a city, this actually I took it from a tender that came out last week from Chennai. Chennai asked for SUMP, and this is the data they have wanted the consultant to be picking up. Household surveys to understand their current and emerging travel needs. And then classified cordons, cars, buses, public transport frequency today, and the occupancy of each time of the day. Public transport onboard passenger survey, parking surveys, and of course, OD surveys, and then speed and delay surveys. Then terminal areas for making sure that terminal area study, because how many people coming through one particular way are going to get into buses, how many are going to get into cars, how many are going to take rickshaws, how many are going to use their own automobiles. We have to understand this. The pedestrian usage surveys, update of road networking inventory, road safety survey, pollution emission monitoring, and of course, road hierarchy mapping. When you do SUMP, you start looking at everybody's requirement. These are some pictures from Ahmedabad, I think. There is a school here, and they made sure that there is a safe passage available for children to the school. And there is a safe path for bus passengers when they come out of their BRT. And they make sure that, you have a footpath going, and by the time you come here, you have to get out. And when you get out, there is a ditch. These kind of things will get, addressed in a SUMP, and there will be a smooth passage available with a continuous cycle track or footpath or anything. The difference between the objective and measures, how do they differ? How do they actually do?
आज सर नहीं आए हैं ना जीएम सर? कितने बजे से? कहाँ मीटिंग है?
Optimization of for that side, there are phone. Optimization of private transport. Earlier we used to look at private transport optimization. Today it is road network optimization of road network for both private and commercial transport. Public transport first strategy. You include more MRTS, BRTS, and all that. Efficient walking and cycling. Focus on mobility in close proximity. I found even in in the city of Thane, at every bus stop, they started putting up for them, the way to take it and, handle it, the maintenance of it, all that you don't know. You go to Barcelona. Barcelona is a city where there's the housing complexes are on the top, and the main commercial and business CBD is at the down end. So in the morning, people take the cycle from the cycle stands, and it's a downstream, and they keep on coming down all the way down to the city for work. They keep their cycles there, and then they go for work. And in the evening, nobody takes a cycle to climb up. They all take trains. So, and these cycles are all get transported by the city authorities into the back there so that they get it again for the next morning. See, this is the way it has to get the end-to-end connectivity for anything that you need. I mentioned it as a special example, which was actually very, very interesting to watch. Similarly, cycle use is very high in cities like Amsterdam and many European cities, and you will be surprised to find the cycle tracks in say Amsterdam Central. I think they I don't know, they may be parking maybe 1 million or 500,000 vehicles, cycles. Optimization of sustainable transport modes, focus on improvements for public transport, walking and cycling. High mobility cost, if the objective is the high mobility cost, stress on better connections, transport modes and electric mobility. This is the reverse traffic pyramid. You are walking and running is the easiest and best way method. Cycling is the next. Utility bicycles are the next. Public transport comes next. Taxi and transport. Then comes car sharing. Then comes own car. Then comes flying. This is how the traffic pyramid, the reverse traffic pyramid. Now, India's urban transportation policy. This is NUTP, National Urban Transport Policy, is something which is documented, available from the Urban Department of Government of India. You can just go there and download it. The objective are ensuring coordinated planning of urban transport, ensuring integrated land use and transport planning, people-focused, equitable allocation of road space, investments in public transport by non-motorized modes, strategies for parking space and freight traffic movements, establish a regulatory mechanism that will ensure equitable distribution of resources, innovative financing methods to raise resources, promote intelligent transport systems, cleaner fuel and vehicle methodologies. Projects to demonstrate best practices in sustainable management and transport, build capacity to plan for sustainable urban transport. Now, these are the indicators. When you make a SUMP, you actually end up making an indicator for you for the target period of 5-10 years, not more than that. Today, this Nagpur Comprehensive Mobility Plan, when it was developed a few years back, this is how it looked like. Average speed of the network is currently 27, and which they wanted to make it to 35. Like that, each model share of public transport, they wanted to change it from current 10% to 30%. Model share of non-transporterized, that is cycles and bicycles, to 60%. Accessibility of walking, 8% to 40%. Work trips, traveled less than 15 minutes. Total number of trips, bus fleet, they have number of buses for 100,000 population, 1 lakh population was 8. They wanted to make it 50. Walkability of footpaths, 70% to 100%. Bikeability, cycle paths, it's not there, none. They wanted to make all roads, every road to have a cycle path. And also fatal accidents. They have had 10 people of force, 9.59 people for 1 lakh population. They want to reduce it to 0. That is quite. This was the mass transit system planned. BRT corridors, LRT corridors, traffic management center, transport hub, all were planned for Nagpur when they developed their SUMP. Now I'll quickly go through some practical suggestions and comprehensive collection of data, evaluation and representation for street network. You have to collect all this information: footpath, cycle track, right of way. In streets, you need to work out locations of regulated parking, locations for existing public off-street parking, occupancies of on and off-road parking areas in major business districts, key crash locations, black spots, what do you call? And for public transport, you have to identify the major bus corridors, major paratransit corridors, rapid transit corridors, peak hour public transport frequencies per direction on major corridors, peak hour occupancy counts per direction on major corridors, buffer showcasing within 5-minute walk of frequent public transport services, buffer showing areas within a 5-minute walk of rapid transit service. And of course, this is standard thing. Integrating land use with travel, compact developments with good mix of social and economic functioning, minimize requirements of public. We make big townships, and all these townships, all the children have to go to school which are far away, and township do not have, maybe not even have a good kindergarten even. All children have been put into buses and spend time hours on the road. Even hospitals, clinics, everything comes at the other end of the city. This is what SUMP should address. And the vicious circle of automobile dependence. This is a very famous thing. You get car traffic, land use for the roads, emissions, traffic increase distances, reduced attraction to pedestrian and bicycle, shift from pedestrian to car, again car traffic, and this keep on coming like this. So if you don't have good pedestrian and other mobility, people start getting into car. In India, compared to other cities, these developing economies of India, China, Bangladesh, Sri Lanka, all these places, the number of two-wheelers and the accidents, 44, I believe 60 or 50 to 60% people who die on Indian roads today are two-wheeler drivers. And the traffic, volume of traffic, they say in Delhi they have 30 lakh, 40 lakh vehicles, but more than 60% of them are two-wheelers. And the two-wheelers contribute so much into the pollution and road space. All this because our public transport system failed us. Evaluating alternative scenarios is another thing. This is indicating the transport goals. Alternative scenarios, when you are looking, you have to urban indicators with sustainable transport, urban mobility planning indicators with sustainable transport goals. You have to have a transport system at the end of the day in the country or the city that you're talking about, which is harmonized together. And there has to be a transparency that is available in the evaluation metrics. And the data collected has to be multiple times reconciled. Time horizons that you talk about when you're developing a sustainable urban mobility plan. Rapid transformation takes place in developing cities. Should be wary of long-term projects, 5 to 10 years instead of 20 years, or for only 5 to 10 years. Also, cost control, overruns, close monitoring of indication. important, one of the is stakeholder participation in UAV preparation. In one of the earlier slides, we said earlier transportation planning was left to traffic and transportation experts, and nobody else involved. Timeline case. Today, it's a multidisciplinary thing. You have to involve stakeholders in participation of the programs, include citizens and interest groups, and this will avoid delay due to public agitations and people expect public consultations prior to expensive investment decisions. So you people carry now public and even public political representatives of the public. They make sure that every public is consulted to the extent possible before they make expensive investment decisions. Include large amount of surveys, public consultations, use internet as a platform to get creative feedback from all citizens. Proper planning of public interaction and their legal and organizational limits to be understood in advance. Yes, any questions? Hello, everybody sleeping?
Yes, sir.
No, sir. No, sir.
All right. So let me thank you and close this presentation and come to a face-to-face meeting with you possible.
Sir, thank you, sir. Thank you.
So nobody have any question, or everybody understood everything, or nobody understood anything?
Everybody understood, sir.
The topic that I handled varied at very different subjects, starting from basic data to urban, macro planning of a city development and things like that. So it is natural that we have a problem of understanding for different people. But I hope I could do some justice and cover all the points to some satisfaction of yours. Yeah. So anybody have any comment? It's welcome. Other question or comment, please.
No comment, sir. Thank you, sir. Thank you.
All right. So shall we close?
Yes, sir.
Yes, sir.
All right. Thank you very much, and good spending a good morning with you all. Neeraj, can you just say a few words and close this presentation?
So thank you so much, sir.
Thank you, sir.